They say that you can't teach an old dog new tricks, but can a plant teach nuclear to show a gentler side? And if it can, then what does that mean for the future of energy? That is the challenging question that we're going to be tackling today. And we're going to be talking about some cutting edge stuff, but I don't want you to get scared if you don't know much about physics. I have specifically prepared this video for you, but the people who do know a bit about physics, every now and again you will see this emoji symbol, and that's your opportunity to go down into the description where you can find the appropriate timestamp and links to more information. Ultimately, I want this video to be, in a sense, a conversation starter for what's possible, potentially, with nuclear today. So, let's get started. Gentle nuclear, it is an oxymoron for basically everybody. Say the word nuclear to the general public and it will conjure up images of Fukushima, of Chernobyl, Nagasaki and Hiroshima. These are events that have been seared into our collective awareness for a very good reason, because they show the ferocious nature of nuclear power, the total opposite of gentle. And even if you are a nuclear physicist, you would still struggle with the idea of a gentle nuclear process. Now, why? Why is it that we struggle with this idea so much? And it's really because of a mindset which says we can never be in control of the nucleus. That in the core of every atom where this immense power source exists, it's essentially beyond our ability to influence and engineer. And the result of that mindset is nuclear radiation, which is kind of, synonymous with nuclear power, is seen as inevitable, as natural, as something that we just have to deal with. But do we? It seems like the answer might actually be no. And that means nuclear without radiation, a completely different prospect to the nuclear that we have come to know about. And so how is such a thing even remotely possible? That is what we're going to be digging into more next. But before we can dig, we need to get on the same page with what we specifically mean by radiation. Because it's not obvious, and for a lot of people, radiation is just this scary thing that they want to stay as far away from as possible. But as with most things in physics, it's subtle. In this case, there is bad radiation, but there's also good radiation, some that's essential for the functioning of our body. Determining what's good and what's bad is complicated, so what are the highlights? Let's start with the bad. The bad stuff for us comes from the core of an atom, the nucleus, and it comes in the form of neutrons, which are uncharged particles that get shot out of the nucleus at great speed. And there's also gamma rays. This is essentially just high energy light. And the reason that neutrons and gamma rays are problematic for us is that they are highly penetrating. You need meters of concrete in order to shield against them. And eventually when one of those things hits an atom in a DNA molecule, it can knock off electrons, causing the DNA to mutate, and that's what gives you cancer. Nobody wants that. What about the flip side, the good side? Well, we've said that gamma rays are just high energy light. Well, that means that light, like visible light from the sun, from a lamp, from your laptop screen, that's also radiation. It's called electromagnetic radiation, and there are a whole bunch of different kinds of it, depending on the type of energy. So the highest energy is gamma rays, that's what we've just talked about. Then next down in energy is X-rays, great for scans, can also give us cancer. Ultraviolet's next down, also can give us cancer, but some of it is essential for making vitamin D in our bodies. Visible, we know about that. Infrared, that's otherwise known as heat. Then you've got microwaves, great for mobile phone communication. Don't want to stick my head into a microwave oven though, so you can start to see where the subtleties come in. And then you've got radio waves, which everybody knows and loves. So that's a very brief introduction to radiation. We don't want the neutrons and the gamma rays. Ideally, we would like the energy to come out of the nucleus in another way. But how can we do that? Well, we are going to ask for the help, and we're going to take inspiration from, in a sense, the masters of radiation manipulation. Trees, which are amazing. They are the lungs of the planet, ecosystems for countless species. They turn light radiation into food. Incredible. But what you might not know about trees, and indeed all green plants, is that they are quantum machines. And no, I don't mean this kind of quantum machine. I mean a moist and squishy quantum machine. You see, long before we were busy tinkering with quantum computers, nature had, of course, figured out how to master quantum, but not from the perspective of processing information, but processing energy. And they do this by manipulating light radiation on the atomic scale, which is tiny. And just to give you a sense of that, if you were to compare the size of an atom to the size of an apple, it's like comparing an apple to planet Earth. It is a tiny, tiny scale, the atomic world. Okay, but why do you need to know that plants use quantum physics to make their food? Well, it's because we're interested in manipulating radiation on the nucleus. Now, the nucleus, which is part of the atom, is just mind-blowingly small. So think of the nucleus as like a pea in the center of a football stadium. That gives you a sense of how small the nucleus is compared to the atom. But nevertheless, quantum physics works the same on the atomic scale and the nuclear scale. And so it's very likely that what we will learn about how plants use quantum physics to manipulate radiation on the atomic scale will work on the nuclear scale as well. And so that gives us the kind of motivation to continue digging deeper. So let's figure out how it is that plants make their food. There's two main steps. The first is the plants need to absorb the light radiation, and they do this using a bunch of chemicals, the most famous of which is called chlorophyll. That's the green stuff that leaves are made of. The second thing is they need to just transport that energy from where it's absorbed to where it's needed. And this is very similar to coal, right? You dig it out of the ground, but it's kind of useless unless you can transport it to the power station. But for the plants, this transportation process is actually a race against time, and that's where the quantum physics really starts to kick in. You see, when light radiation gets absorbed by a molecule of chlorophyll, it excites the chlorophyll, it supercharges it, it gives the chlorophyll a power-up. But what we've learned from quantum physics, and indeed what Einstein taught us in 1917, is that these power-ups, these excited states, they don't last for long. They are unstable. And within a billionth of a second or so, the light radiation that is absorbed just gets re-radiated back into the environment where it's lost to the plant. So you can see plants really have to work very hard, very fast in order to harvest the light energy. But of course, they figured out how to do this by jam-packing the chlorophylls into these little green circles called chloroplasts. And in these chloroplasts, the chlorophylls are so close together that they can interfere with each other in, we say, a quantum way. Now, what does that mean? Well, it takes advantage of an unintuitive duality in nature, that everything can simultaneously behave like a particle, but also like a wave or a ripple at the same time. And the kind of end result is there's a kind of quantum collaboration between all of the chlorophyll molecules, and they end up behaving in a sense like a collective, coherent whole. And in that state, energy gets transported from one side to the other at lightning speed. We're talking a trillionth of a second or less. It's just crazy, crazy fast. Now that process that plants use is called resonance energy transfer. And plants have utilized this to, in a sense, avoid the inevitable, which is re-radiating that light back into the atmosphere where it would be lost. Now, we've heard about inevitability already, nuclear radiation. So this is the appropriate moment to make the connection back. And we can do that by asking a question. Why is it that elements like uranium are radioactive? They give off radiation, whereas others like helium don't. Well, it's because the nucleus of uranium can be considered to be in an excited state. And we've learned about excited states already in the atomic world. Einstein told us they're unstable, they don't last for long, and eventually they'll give out radiation. So that's where the gamma rays and the neutrons come from. But the question is, do we need to have them? We've just learned from the plant world that there are mechanisms, at least on the atomic scale, to avoid radiation. So it's not crazy at all to imagine that similar processes could be at work on the nuclear scale as well. And if we can find those processes, if they exist, then that's the beginning of controlling the nucleus, of having nuclear without radiation, which is what we want. But of course, I'm skipping a lot of details there necessarily. So what can I tell you in the meantime to, let's say, whet your appetite? I can tell you that even since the 30s, people recognized that the nucleus was not as isolated as it seems, that it is, in a sense, sensitive to its atomic environment and beyond. And also more recently, a lot of groundwork has been done on the detailed mathematics of the quantum physics, most notably with the work at MIT, which has been going on for a long time, so well over a decade, and that continues to this day. And it's not just in theory, but also experimentation as well. So the last couple of years, there's been some incredibly promising experimental results coming out of MIT. So it really does seem like we might be able to, in some sense, engineer the nucleus. But of course, I should be careful because this is still, very frontier, very cutting-edge science, and a lot more work needs to be done. Experiments need to be refined, theory needs to be expanded, and in some sense simplified, because the quantum physics is notoriously tricky, and also we need to communicate these ideas to a less specialized audience. And we need to do that because ultimately we want to grow a gentle nuclear network. That's the only way we can fully realize the potential of this field. And that's actually a lot of the work that I've been doing over the last few months with people at MIT and elsewhere. We have built an open science platform called Project IDA. And the aspiration, in a sense, for this platform is that it will be the hub for this emerging field of solid-state nuclear science. So please do go check us out and get in contact if you are interested to get involved. We are very friendly people. So gentle nuclear. By this point, I hope that I have convinced you that this idea is worthy of your attention, and maybe I might have created a gentle nuclear advocate in you. But you're probably thinking, well, what's this going to do for us at a societal level? And it's a good question. I don't think we are fully ready to answer it yet because we've been in this conventional nuclear box for so long, and we're only just starting to peek out and see the possibilities. But what I can say, which is slight speculation, but I think it's worth talking about the potential possibilities, is nuclear waste should be just a thing of the past. Either because we can use this kind of quantum speed up that we've heard about in the atomic world from plants to just reduce the time the waste is sitting around, or maybe we don't even need uranium at all. The periodic table is big, so why can't we consider pairing up elements in a smart way, creating novel nuclear reactions that don't give off harmful radiation in the first place? Those two ideas by themselves would be incredibly impactful in the world of nuclear energy. But we can go further, because once you open your mind to the possibility of engineering the nucleus, the sky's the limit, right? You can set your sight at the grandest of challenges like nuclear fusion, which is the process that goes on in the center of a star, and the idea is mimicking that process on Earth to provide limitless clean energy. But it is a fiendishly difficult task that requires temperatures 10 times hotter than the center of the sun, 150 million degrees Celsius. It is no small feat, I can tell you. But it seems like, and it's not obvious from what we've said here today, and it needs another video, but the physics of this resonance energy transfer might have an impact on fusion as well. And that means maybe we can have fusion that's more feasible at lower temperatures in a compact way. And that is just tantalizing. It makes me think about a decentralized world powered by fusion batteries that will give us true energy independence. And that is what, gets me up in the morning. That's what gets my blood pumping. It's exciting. And you will probably want to know more about that and the details of everything else we talked about here today. I'd say that we've probably done enough casual physics for one day. Please do stay tuned. I will go into the details of all that stuff in future episodes. So as always, thanks for being here. I really appreciate your attention. I look forward to seeing you next time. See you soon.